Hello, this is Deborah Chung at Buffalo. I'm very happy to share with you smart structures, self-sensing, energy generating, and shielding. I was born and raised in Hong Kong. I'm the little one in the family, a very beautiful place. But in 1969, the first person landed on the moon. I was still in high school, and I was so inspired that I decided to leave Hong Kong for America to study science. And I went to Caltech, very good school, and I became one of the 4 first woman graduates of Caltech, and also the very first woman engineering graduate. I got interested in integrated circuits, and I studied under Professor Carver Mead, the father of very large-scale integrated circuits. However, I did research under Professor Dewey, the father of amorphous metals, and that was my very first taste of research. And research is not merely finding out the existing knowledge, but it's creating knowledge so as to advance human civilization. Materials in particular can be very pretty, and also a lot of applications such as electronics, aerospace, biomedical, as well as construction sectors. Materials actually constitute the foundation of any technology, electronics, aerospace, automobile, and whatnot. Also, materials mark the history of human civilization, starting with the Stone Age, Bronze Age, Iron Age. It's really exciting to be driving on the road of human civilization. It's not on the back seat, but on the driver's seat. After graduation from Caltech, I moved on to MIT for my graduate work, and I got interested in graphite. Beautiful arrangement of carbon atoms in graphite, also applications in batteries, in aerospace, such as carbon fiber. Carbon fiber composites are widely used for aircraft because they are lightweight as well as strong. And I studied under Professor Millie Dresselhaus, a very prominent carbon scientist. She was a solid-state physicist. And we decided to study the reaction of graphite with certain strong chemicals so that the strong chemicals go in between the graphite layers, making a sandwich compound called an intercalation compound. And in so doing, the graphite becomes a metal. It's very interesting, changing graphite to a metal through this process, which involves charge transfer. And I continued this line of research for 10 more years after graduation from MIT. And I gradually saw the decline of my field of expertise because the applications did not quite work out at the time. So I decided to leave my field of expertise, but what to do? That's the big question. So I was forced to think out of the box and leave my comfort zone. And I got interested in cement and concrete, something I never studied before. And because of my electrical background, I started studying concrete as if it's an electronic material. And thus, I invented smart concrete, which contains a little bit of short carbon fiber, which alters the electronic properties. And the idea is that, say you apply a load in the smart concrete, the electrical resistance changes. And so by measuring the resistance, you can tell how much is the deformation, also the damage. And this is known as self-sensing. That is the structural material sensing its own condition without the need for any sensor incorporation. And this makes possible real-time monitoring, which is better than occasional monitoring. Now, if one embeds a device like a sensor into concrete, it looks something like this. And if the device malfunctions, it'd be pretty hard to repair that. But without device incorporation, we have low cost, high durability, large sensing volume, and the mechanical performance not being compromised. Numerous applications, such as building intruder detection, that is detecting the intruder because the intruder weighs something, so no camera needed. Also weighing trucks as they move, and traffic monitoring, again, because the vehicles weigh something. Autonomous vehicles need a lot of sensing, not just cameras and radars, but the infrastructure being able to help the sensing would be very nice. Bridges and high-rise buildings need vibration control because of the wind. Here, this bridge in Minneapolis fell down some years ago, and some people died. And this building in Miami collapsed suddenly, and a lot of people died. And this dam partially failed, and that results in at least one building swept away by the water. And all these structures were built by using steel-reinforced concrete, seemingly a very matured technology, but in fact, it's full of problems. Now, concrete has a structure which involves stones and sand acting as reinforcement that's bound together by cement. And this cementitious bond is not a very strong bond. And so one needs to embed in the concrete steel reinforcement. However, the steel can get corroded, especially if the structure is near water. Now, if we look at Niagara Falls, which is close to my home, it's a different ballgame. Very forceful water, and the water actually touches the rocks, but very durable, no problem, century after century. So nature's technology is actually very advanced. Now, oil gas wells, another problem. In all these wells, you have cement doing the sealing between the rocks and the steel casing. And if the cement sealing goes bad, you can have leakage and oil spill, causing pollution as well as birds suffering. So it's a big deal. And it's important to be able to sense the condition of the structure. Another cause of degradation of concrete structures is freeze-thaw damage. And that is because water expands upon freezing, and there's water inside the concrete. So if you have multiple cycles of heat, freezing and thawing, it's like fatigue, and the concrete can degrade. And conventionally, people study freeze-thaw degradation by having this chamber, which provides the temperature variation, and then studying the residual compressive strength after so many cycles. However, I used resistance measurement to monitor the freeze-thaw degradation in real time. And shown here in thin line is the temperature, and the full line is the resistance. Whenever the temperature increases, the resistance goes down, and that is simply because there are interfaces in the material, and increase in temperature would increase the thermal energy, and so makes the jumping of the electrons across the interfaces easier. And so the cement-based material is a thermistor, a temperature measuring device. But in addition, you see the upper envelope and the lower envelope increase as freeze-thaw continues. And that is because there's minor incremental damage inflicted in every freeze-thaw cycle. And just at the end, when it dies, the resistance goes up to like infinity, and that occurs at the coldest point of the last cycle. This is the first real-time monitoring of freeze-thaw damage in cement-based materials. And I found it very fruitful to marry electrical engineering and civil engineering. Very few people join these two fields together, but I find this to be just my cup of tea. Now, smart structures include civil structures, such as buildings and bridges and pipelines and so on. It'd be nice to be able to monitor the condition. Aircraft, same deal. One wants to make the aircraft smart, a bit like people. You know, a human being has nerves, and that's like sensors, and has brain, which is like the computer. So the hope is that we get structures to be a bit more intelligent, although not quite as intelligent as human beings. Now, continuous carbon fibers look like this, commercially available, and they are widely used for aircraft, also for cars and for bicycles, for wind turbine blades, for robot arms, for golf clubs, for tennis rackets, for fishing poles, and for many parts, and also for retrofitting concrete structures. Now, carbon fiber composites are most often in the form of laminates or plies. Each ply is called a laminar. And the interface between the plies is the weak link. This is a microscope view of two plies with the interlaminar interface between them. Now, this aircraft fell from the sky to New York City, killing over 200 people. One problem was that the tail came off. The tail was connected to the body of the aircraft by fastening, that is, nuts and bolts. Well, sounds like a mature technology, but that was the problem. And it would be nice if we can monitor the condition of the fastening so that if it gets loose, one would know that. Now, the carbon fibers in a composite are never perfectly straight. They're always a little bit wavy. As a result of the waviness, the conductivity in the vertical or through thickness direction is never zero, even though the matrix polymer may be insulating. Okay? And so there's always a degree of fiber-fiber contact across the interlaminar interface. And so the contact resistance of that interface is never infinity. And the contact resistance would go up upon delamination. And so this is the contact resistivity versus time during temperature variation as shown in the bottom curve. And the upper curve is the contact resistivity. Every time one squeezes, the contact resistivity goes down, and that is because one is increasing the proximity between the fibers of the adjacent laminae. However, note that upon unloading, the resistivity doesn't return all the way back. That means there is some degree of irreversible microstructural change. Could be very, very minor damage. However, if we replace this very conventional epoxy matrix with a thermoplastic matrix, such as nylon, see, upon unloading, the resistivity returns all the way back. Okay, that's very good. And it's because the thermoplastic, like nylon, has polymer chains like that, and they can slide easily with respect to one another, so it's pretty tough or ductile. But for the epoxy case, it's brittle because of the cross-linking between the chains. Another nice thing about the interlaminar interface is that you can have an array of interfaces. Here you have fiber groups and XY, and you have a junction, and so you have an array of junctions, and that's an array of interfaces, meaning an array of sensors. And thus we can do 2D spatially resolved sensing. In addition, the fiber groups, in this case XY, it provides a grid of electrical interconnections. Now, robots also are smart structures, and you need sensing, actuation. So a lot of the concepts that I talk about are applicable to robots. I remain interested in electronics, and one of the biggest headaches in the electronic industry is the overheating of microelectronics and cell phones. And the microprocessor is the heat source, for instance. And if it goes bad due to the overheating, you might need to replace the chip. So it's a reliability problem. Also, overheating limits further miniaturization because the smaller it is, the more concentrated is the heat. And also overheating limits the electric power because the more is the wattage, the more is the heating. So we must get heat dissipated. We use the heat sink, obviously, but the thermal contact between the heat sink and the microprocessor can be a problem. If this thermal contact is not very good, you're not using the heat sink very well. So people put in a thin layer of thermal interface material at the interface so as to improve the thermal contact. And this is an example of a thermal interface material, which is in the form of a paste called thermal paste. Now, all along, people have been assuming that high thermal conductivity is the criterion governing the performance of a thermal interface material. But I figured out that it is not the criterion. There's another criterion which is just as important. And that is because no surface is perfectly smooth. So there are microscopic ups and downs, and air resides in those microscopic valleys, and air is a thermal insulator. So the thermal interface material has to be able to conform to these ups and downs so as to displace the air out. So the conformability is crucial. Even if the thermal conductivity is very high, if the conformability is not good, that material is not going to function well as a thermal interface material. And realizing that and knowing that carbon black is itself a solid that is conformable, I ended up inventing carbon black thermal paste, which excels due to the conformability. Now, carbon black has a nanostructure involving aggregates of nanoparticles, and it's like little filaments sticking out like an octopus, and it's just van der Waals forces linking these nanoparticles. And so when you compress it just a little bit, it's going to squish. It's squishable. And because of the squishability, it's very conformable, even in the solid state. So I put forth this new concept and therefore brought forth a paradigm shift in the design of thermal interface material. Used to be just thermal conductivity. Now there's a paradigm shift so that the conformability is just as important. Let me now switch to shielding, electromagnetic shielding, mainly in the radio wave and microwave regime, because such waves can interfere with computers. So we need to shield computers and other electronics, also to shield the radiation source, such as cell phones. Metals are widely used for shielding because they are high in conductivity, and the high conductivity promotes shielding by reflection. However, there's another concept that's important, and that is the skin effect, which means that the radiation penetrates only the near surface region of a conductor. And so high surface area would promote shielding. So if you have a composite with a polymer matrix which is not conductive, and you have conductive filler in the form of these short fibers, let's say. And if each short fiber is big and fat, only the surface region of each fiber unit sees the radiation. The inside just sits there doing nothing. So at the same volume fraction of the filler, having a nanoscale filler would be much more effective for shielding than a microscale filler. And so I realized then that the surface area or interface area is very influential. With nanotechnology being more and more commonplace, the use of nanofillers become more and more feasible. And shown in the left is a microfiber, that's the usual carbon fiber. On the right is carbon nanofiber. And we show that by going from micro to nano, we can improve the shielding quite a lot. This shows the carbon nanofiber, low MAC here and high MAC here. But we can improve this further by depositing nickel onto the carbon nanofiber. The nickel is a metal, so it's very conductive. Also, it's magnetic. And this is low MAC and high MAC view of the nickel-coated carbon fiber. And this we reported back in 1995, and it's still among the very best fillers for EMI shielding. Another direction of exploiting a high surface area is to use graphite flakes. One can intercalate the graphite flakes to make that sandwich compound, and then rapidly heat it, and it would puff up, and like popcorn, and that we call that exfoliated graphite, as shown on the right. And each piece of exfoliated graphite emanating from a flake looks like a worm, and it has a cellular structure. Okay, and this shows a higher mag view of this cellular structure, a part of a worm. And if we have a pile of these worms and compact this pile, because of the cellular structure of each worm, there is mechanical interlocking among these worms. So it forms a sheet without any binder. It's all graphite. And this sheet is flexible, so it's called flexible graphite. And we discovered a long time ago that this material is superb for shielding. 129 dB of shielding. That is the highest you can measure. So we brought about a paradigm shift in the design of EMI shielding materials. It used to be just electrical conductivity as the only criterion. But now we realize that there's a second criterion, that is the surface or interface area being high can help a lot. Now, power transformers need shielding. Any electronics need shielding. And power transformers, big ones, are underneath the road and contained in a concrete vault. And this is inside the vault. And so we would benefit from concrete that can do shielding. And concrete itself is not effective for shielding, but we can throw in some conductive additive called admixtures into the concrete mix to make the concrete conductive and thereby be able to shield. It's not only for protecting electronics, it's also protecting everybody in case there's a nuclear blast at high altitude. And that blast can give off very strong radiation that reaches the whole of the United States. Is a very big deal. They call it EMP, or electromagnetic pulse. And so people have buildings like this to protect against EMP. And the concept is just like shielding. And here is a rendition of a luxury bunker that provides the EMP protection. I was the first that reported about cement-based materials being able to provide EMI shielding back in 1989. And since then, I've improved. Short carbon fiber inside the cement-based material, 26 dB. But if one goes with short steel fiber, it's a lot better, 70 dB, because the steel is a metal, it's very much conductive, and also it has some magnetic character. But note that both are microfibers. That's important. If it's nano, it's even better. But these are micros. And if one uses the macro fibers, it would not be effective. And microfibers are used because of the skin effect. Another application is automatic highway. We'd like to have automatic steering. And one way to get that is to pave along the traffic lane of the highway, say the middle part being radio wave reflecting concrete, and the rest is ordinary concrete. And each car should have a transmitter and a receiver of radio wave. And so if the car sways to the side, then it would know that. And I have a wonderful time marrying microwave engineering and material science. And this is a marriage that is not usual. Microwave engineers don't tend to look into material development, and materials people don't tend to touch microwave. But to me, that's my cup of tea. Another topic that's dear to my heart is vibration damping. Now, we'd like a structure not to vibrate. No, just being able to bear load is not enough. You'd like it not to vibrate. Bridges need vibration damping. High-rise buildings do also. And railroad need vibration damping as well as sound absorption. And sound is a pressure wave. Aircraft also needs noise reduction. And satellites obviously need vibration damping. Viscoelastic behavior of materials is the key to vibration damping, like ketchup and rubber band. And the idea is that, say you have rubber, and inside the rubber there are long, long molecules. And when you deform the rubber, there's motion of these long, long molecules, and that motion consumes mechanical energy, thereby reducing the vibration. The stress-strain curve upon loading doesn't overlap that during subsequent unloading, and so there is energy dissipation. The bigger is this hysteresis loop, the better. This is viscoelastic behavior. Polymers like rubber are well known and utilized a lot for vibration damping, but there are serious disadvantages because they are low in stiffness, low in strength, and also poor in durability. Rubber bands cease to be elastic after maybe a month or two. Okay? However, my dream is revolutionary, using structural material for vibration damping. It's something that nobody has ever thought about. The advantages are high durability, high stiffness, and large volume. Now, the large volume helps a lot because this hysteretic area is the energy dissipated per unit volume. Okay, so if you have a big volume, it means a lot of energy dissipated, and the structure is big. And I had to devise a different mechanism of viscoelasticity. The usual mechanism exhibited by rubber is not good enough. And the mechanism I devised involves slight slippage at the filler matrix interface. I don't mean loosening the interface. It's just very slight reversible slippage during the vibration. And there's friction involved. And so this slight slippage consumes some mechanical energy, thereby providing mechanical vibration damping. And this I call interface-derived viscoelasticity. It is not due to the bulk viscous deformation that rubber provides. But for this interface-derived viscoelasticity to be substantial, there must be a lot of interface. But a lot of interface can be realized if one uses nanofiller. Okay? So I use nanofiller in the form of silica fume, silica particles, and put that into a cement matrix to form a composite. And because it's nanoparticles, you have a lot of interface. And that's it, it makes possible this interface-derived viscoelasticity. In addition, the nanoparticles serve as reinforcement. So I'm stiffening the material in addition to making it better in damping. So improving both stiffness and damping, that's revolutionary. People could not believe me when I reported that back in 1998. Because people have rubber in mind. If you have a type of rubber that is stiffer, it's going to be less good for damping. You gain one and lose the other. But here, I gain both. How about my new dreams? Electrical properties include conductivity, permittivity, and inductance. Let's look at inductance. I term it structural inductance. That is, structures providing inductance-based function. Inductors are conventionally in the form of metal coils. And inductance is the tendency of an electrical conductor to oppose a change in the electric current flowing through it. And inductors are used in electronic circuits, also in power transformers, in electric generators, and electric motors. Almost 100% of electrical energy in the world is produced by generators, and motors consume about 65% of the electricity. And what I'm interested in is not those coils, rather uncoiled materials as inductors. This is an emerging field of science. It's good to have no coiling because that would make it more compact and it can allow structures to do the job. And so I call it structural inductor. And that's a new functionality, a new level of smartness for structures. A single carbon fiber has a cross-sectional morphology looking like this. It consists of carbon layers that are crooked, bent. And because of this nanostructure within a carbon fiber, even though the fiber is straight and coilless, the fiber can have substantial inductance. And we discovered just recently that the single fiber inductance is higher than the value calculated based on the dimensions by a factor of 1100. Okay. And the inductance reaches 0.4 millihenry with just a short length of the carbon fiber. Now, millihenry is actually a pretty high inductance. Permittivity is another kind of electrical property. Electric cars need batteries, okay, and the batteries take up volume as well as weight, and limits the payload and increase the fuel need. The aircraft in the form of vertical takeoff and landing is all electric, need high agility, and it's supposed to act like an air taxi traveling within the town, and so it needs to be quiet, and therefore has to be all electric, and this demands the energy tremendously. So structural battery or structural capacitor means making a structure provide the battery or capacitor form of energy function. And the idea is not embedding a battery, not embedding a capacitor, but rather modifying the structural composite so that it can do the job. Okay? I was the first one to report on that back in 2001, but I was not very excited about this because this modification, even though it's not embedding a battery or embedding a capacitor, it requires modification of the composite, and the modification weakens the mechanical behavior of the composite. And you must maintain the mechanical property of a structural material. And also, the service life of this, the battery function or the capacitor function is a lot shorter than the service life that's expected for that structure. So I looked into, recently I looked into a different route, altogether a different approach. And I call that structural permittivity. That is structures providing permittivity-based functions, including energy function. Permittivity relates to the polarizability, separating the positive and negative charge centers. And permittivity is very much studied decades for insulators, such as polymers and ceramics. And one can measure the capacitance and the permittivity as well as and as a result the capacitance, which relates to the permittivity, would be affected if there's a defect in the material. So we use capacitance-based defect self-sensing in 3D printed polymer which is not conductive. And we had 7 dots representing 7 artificial defects placed at certain positions between certain layers. And we measured the capacitance using these 2 electrical contacts, and we were able to figure out the number of defects. Is it 1? Is it 7? And also between which layer the defect is located. However, recently we made a very revolutionary step, is to extend the permittivity or capacitance concept from insulators to conductors. Sounds crazy, but actually, after a lot of literature research, we found that Johnscher, back in 1999, predicted that in high conductivity materials. By theory, he predicted. And the prediction is that the permittivity of high conductivity materials can be very high as 10 to the 8. Okay? Unfortunately, he passed away 6 years after the prediction. And 20 years after the prediction, that is 2019, I made the first experimental observation of such huge permittivity in conductors, such as metals and carbons. Concerning capacitance-based self-sensing, then we can apply that to both conductors and insulators, as long as the material is polarizable. Okay. In contrast, resistance-based self-sensing, which was what I did involving smart concrete, the resistance-based self-sensing is applicable to conductive materials only. So the capacitance-based self-sensing actually is more broadly applicable than resistance-based self-sensing. But how can a conductor like a metal be able to provide polarization? If there is no electron atom interaction, then the electrons just loop around the circuit and no polarization occurs. But if a small fraction of the mobile electrons interact with the atoms, then you can have polarization. And that is the mechanism which we found to be indeed the case, the electron-atom interaction. And this interaction we further found to be mainly occurring at the microstructural heterogeneities, such as grain boundaries. And so rolling, the mechanical rolling, for instance, would increase the permittivity because it kind of refines the microstructure. And polarization involves engagement of the carrier-atom interaction, the carrier referring to the mobile charges, and depolarization under reverse polarity involves disengagement of this interaction. And we varied the grain size of polycrystalline graphite, and indeed, the smaller is the grain size, the higher is the permittivity. And if we plot that versus 1 over grain size, we get a linear plot indicating that indeed it's the grain boundaries that matter in the this carrier-atom interaction that's responsible for the permittivity. Now, poling refers to the application of a strong electric field so as to line up the electric dipoles. This is before lining up, this is after lining up. Okay, and after poling, it can randomize a little bit, and that's depoling, which is spontaneous. And the poling is required in order for ceramics and polymers to be polarized. And large structures cannot be poled anyway because it's too large. The voltage required to give a particular electric field would be huge. So structures cannot be poled anyway. And polymers and ceramics, these insulators require poling. But the conductors, like metals and carbons, don't need to be poled. They are naturally poled because of the electron-atom interaction. And so this is single carbon fiber. It exhibits capacitance without the need for poling. Okay, but then if you short circuit the single fiber, the two ends, it would discharge. Okay, with the capacitance going down. Afterward, if you just open circuit it, it would self-charge. That is, it charges on its own, just sitting there open circuited. So it's self-charge. This is really revolutionary, self-charge. Batteries and capacitors, conventional ones, they all undergo self-discharge. And the charge requires energy input, but this is just opposite. The discharge is spontaneous, but the charge is self-charge. This is one application format that we devised, and that is using a fiber assembly. You have fiber 1, fiber 2, and so on. And each fiber, you have a red time period, which is discharge, and then the black time period, which is self-charge. And the start time of the discharge is a little offset between fiber 1, fiber 2, fiber 3, and so on, a little offset. When you have this assembly of fibers, then you have continuous discharge. And so a continuous rendition of energy. This is perhaps our newest dream, and still a lot of work that needs to be done. And note that the time is increasing to the right in this picture. So this brings me to the concept of structural energy, a term that I devised, referring to energy generated by structures. Structural materials include metals and carbons. It can be viewed as a new untapped form of energy. There's no energy storage needed because energy is generated continuously, and no greenhouse gas emission, obviously. I said it already that I was the one that reported for the first time structural capacitor. But I was not very happy with this because the structural performance is diminished due to the modification required. But now this is a totally different approach. It's not modifying composite. It's utilizing the single carbon fiber assembly and offsetting the start of the discharge for each fiber and letting each fiber go discharge and then self-charge. In this way, provide continuous discharge. The scope of my research includes structural self-sensing, structural permittivity, structural inductance, structural energy, thermal interface materials, EMI shielding materials, and interface-derived viscoelasticity. What I want in my heart is not just an incremental advance. I want a transformative advance. And transformative science opens a new horizon. I want to be a leader, not just a follower. But creativity is so, so important. Thinking out of the box and able to jump out of one's comfort zone, very important. And having broad education helps that a great deal. And I really cherish the broad basic science education that Caltech provided me. IQ, we all want that, but EQ is emotional quotient. That is the ability to continue to go ahead in spite of difficulties. SQ is spiritual quotient. That is knowing what you're living for, what's the meaning of in life. And we need all three Qs to help us succeed in life. Thank you so much for sharing my fun. I really thank Caltech for the Distinguished Alumni Award in 2025. This is so dear to me that my alma mater would recognize me. I also want to thank my former PhD thesis advisor, Professor Millie Dresselhaus, and he mentored me very, very well. Thank you.